Yeah, there are different ways for modeling the pile and the raft in GTS Unix. So we can consider the normal pile as a beam. So we can consider a beam element, 1D element basically, and then to that 1D element we can provide section properties. So instead of beam, we can consider embedded beam as well. Whenever we consider beam, we need to make sure that this beam element is in contact with the surrounding soil element. And if we consider embedded beam element, then there is no need to worry about the connection with the soil, because embedded beam can able to take the connection with the soil automatically. And then we have a pile plus pile interface. So if you want to generate a realistic scenario, so if you have a pile load test results with you, then you can create the pile interface where using those the test results and using some approximations, we can consider the inputs of the pile interface, where this will help you in determining the skin friction and pile tip. There is one more thing called the pile tip, so that will help you in determining the tip resistance. So that this pile interface will be applicable to this beam element. And there is one more way in order to model the pile, that as pile as a volumetric element. So here, the volumetric element is nothing but the solid element. So we will be giving you the pile as an tetrahedral mesh or hexahedral mesh. And in the first one, when we consider pile as a beam, there is no like a real interface between the soil and the beam. But here, the beam is in rigid contact with the soil. So that's how we consider the pile and the soil if we are not providing interface. But when we consider volumetric element, that's actually the results will be the same, because here also the solid elements are not in in rigidly contact with the soil. And there is one more option, pile as solid elements, that means volumetric pile plus interface. So you'll be modeling the piles as a solid elements, basically volumetric elements, and providing you with the interface. So that's a plain interface. And then we can consider raft, the top of the pile cap or raft, as a solid element, or we can model them as a shell element. So there are many ways to model, and in this session, I will be dealing with the most of the problems in here. I will be showing you how to model each and everything, so that we can find the different results from the different outcomes of different models. And in the results, we'll be interested in seeing the structural forces, axial forces, shear forces, and bending moment. And we'll be seeing the displacement, stresses, and strains. Apart from these three, we will also see the normal forces acting on the piles, the shear, let's say the skin friction acting on the piles. So we'll see all those results in this session. Yeah, now I will be going, I'll be showing you how to model all of these things in FEA NX. So now this pile raft situation is like a 3D model, 3D model situation. We cannot compromise for 2D for a pile raft situation. And now we will go for 3D modeling and the gravity direction sets. And these are our unit systems and initial parameters. These are your water parameters. And let's say, okay. So here in this session, I will be considering different types of pile raft foundations, and I will be showing you all those scenarios in one single model itself. So we'll see how that goes. Let's consider an grid with a size of, let's say, 2 meters. So we have a 2-meter grid. That means from each point to each point, the distance is 2 meters. Now, in one quadrant, I will be modeling the piles as a beam element, and one quadrant I will be modeling the piles as an like beam plus, let's say, pile interface. And in other quadrant, I will be modeling the piles as a volumetric piles by applying interface and everything. So that's how I will be modeling for today, just showing you the different modeling procedures. So let's go for definition of the pile using the line element. So this is the pile. So here we are going for a 3D pile. So the pile will start from here and will go down. So let's go for 3D. and provide the first point, and let's say this will go down for a distance of around length of the pile, basically around 10 meters, and say apply. So this is our first pile, and let's say the distance between center to center distance between two piles is let's say 2 meters. Let's say 2.5 meter or 2 meters. I will select and I will just provide the distance of 2.5 meters. And we say copy, the method is copy. And here we have, and let's say apply. Now we will consider these two piles, and now we will like do in other direction. We will just copy. So right now only 4 piles. I'm modeling 4 piles in this case. So 4 piles. So here we have a 4 piles. And now what we do is we'll be providing an file raft. I'm providing with the random values for today's session, but you hope you understand. Yeah, this is not good. Sorry, I will just delete this. Yeah. So this is for raft, and these are for piles. So 4 piles and 1 single raft. And now we'll be modeling the soil layers. Let's say we have around 3 layers of the soil. The first layer is the medium sand, and second one is sand, and the third one is the soft rock. So we will go with the S-base approach. This is first layer, and in this case, I'm modeling the piles as a beam element itself, or we can consider embedded beam as well. I will show you how to consider beam or embedded beam and so on. So let's extrude the soil. So let's say the thickness of the raft is around 1 meter. A pile. And now we will select our here and select the direction as the direction. And let's say the first layer is around 5 meter depth, and we will just see. Yeah, it's going in correct direction. And now the second layer is, let's say, around 3 meter. And now consider the last layer. Let's say the last layer is around 10 meter. Yeah, so this is how we model. Yes, sir? Yeah. So now here we have a raft, and now this raft is a solid element, and we have 3 solids. And now what I do is I will show you how to model the raft as a solid and as an shell element. But before going to it, I will just provide how to imprint. I will just show you how to imprint the files, the Bundy curves onto 3D solids. So that's the major part I will show you. So right now we have 3 layers of the soil, and one is our raft. So here in this situation, I'm considering the pile as a beam or embedded beam element. And I'm not considering the pile interface. So we are considering pile as beam or embedded beam element. So in this scenario, we need to make sure that each and every part of your line is in contact with our soil layers. So in order to make sure that we need to imprint those lines. So here we have imprint option. Just go to the imprint option, and we go to imprint auto. So select all the solids, and now we will select the tool objects. The tool objects are nothing but your lines. That means the pile curve. I will show you what are the selected lines. So these lines are your piles, So those got selected. So basically these lines got selected in here. Now we will make sure that they got imprinted. So whenever there is an imprinting, then this yellow color icon will be showing you this yellow color symbol that represents that your raft is imprinted, sorry, your files are imprinted to your solid. And now we need to make sure that your soil layers are also in contact or not. So select all, and we will be using auto connect option. And now select all. So all the soil layers are now connected. We'll check the duplicates. So all the soil layers are connected. And now we'll check. Yeah. So here we can see whether there is an imprinting done or not. Using this option, you can see. So here we can see the imprinting has been done, imprinting has been done, and imprinting has been done. So this is not a good approach, considering the file as a beam element, but I will just show you the various methods to model the file. So this is one approach where you're considering the file as a beam element, only beam element or embedded beam element. But whenever you're considering it is a beam element, the soil and the soil and the file are not or rigidly connected. So now what we do is we will define some materials, let's say concrete, an elastic material, and provide elastic modulus of, let's say, 2E7, Poisson's ratio is 0.2, unit weight as 25. So this is for concrete. And now this is for pile and raft. Now we will be modeling our different layers of soil. The first one, let's say we are using medium sand. Let's consider 50,000 elastic modulus and 0.3, and let's say this is an 18 unit weight. And in the cohesion tab, we'll consider, let's say, around the 15 cohesion and the friction angle like around 33. So let's say 31. This is our medium sand. And now we will be using the second layer, and the second layer is dense sand, and I will just name them as dense sand. And for the dense sand, let's say it is around 60,000. Unit weight is somewhere 19, not 19, let's say 20. And since we are not considering water level in this today's session, there is no need to worry about the porous material inputs. And I'm just running the static analysis only. And now the cohesion will be somewhere around 25, and this is 36. So this is dense sand. And now we will be defining the soft rock material. Soft rock, let's say the cohesion as 100 and the friction angle as 38 degrees. And I'm going some random values, and let's say the elastic modulus as 1 lakh kilonewton per meter square, and then Poisson's ratio is 0.2, and let's say this is around 22. And yeah, so these are our different material models. Now we need to define a properties. Now we have we need to define 3 soil layer properties, 1 raft property, and we need to define the pile properties as well. So here we are considering the pile as a beam element. So hence we need to go and define a beam element. So go to 1D, and here we have a beam element. So this is a beam, and we'll consider the material concrete, and we'll give the name as a pile hyphen beam. And here we can go to a section properties, and we can choose our own section. Let's say solid round, and the diameter of the pile, let's say around 0.75 meters. So all the properties will be calculated automatically. And say, okay. Now we got the three solid properties. So let's go for concrete, and we give the name as the raft, which is a solid element. And now we have a medium dense sand. So we give medium sand and say apply. And we have dense sand, and we have soft rock. Yep. So these are the three materials, and I also said that we need to we can model the raft as a solid element, or let's say the shell element. So what I do is I will just consider in a property it's for modeling the raft as a shell element. So just go for shell property, 2D shell property, and here the material is concrete, and the name is a raft, but it is a shell element. And coordinate axis can be considered. You can choose your own coordinate axis, or you can define among these three. So that's all up to us. Let's consider global rectangular. And the thickness of the raft is 1 meter. So that's what we are considering. And let's say, okay. So these are our different materials till now that has been considered. Now we will mesh each and everything, and I will show you how to do that as well. So let's first thing, this is our raft, and we are considering this as a solid element right now. Let's provide 0.5 mesh size and go for hybrid measure and use raft solid. And you say apply. The raft got meshed, and now go for first layer, and let's consider the mesh size as 0.75. Medium sand 1, apply. And now consider the second layer of 1 meter depth, and here we have dense sand. And say apply. Soft rock. Oh, sorry. And say okay. Now we have meshed all the three layers, and we have meshed our raft as well. Then we will go for a 1D element meshing. So we will hide all the mesh steps, and we will select your. And I will hide the rectangles. We are no longer interested in the rectangles. So these are our different lines, and here we will divide in each line into 10 elements, let's say, and pile as a beam, and now say okay. So here we have considered the raft as a solid element, and we can see those are in rigidly connection with each other, and there is no interface at this point. So with this thing, we can consider the soil and structure interaction to be rigid. And now we have a medium sand, and again it is rigid. So each node of your raft, sorry, each node of your soil, not each node, the node of your soil and the node of the pile are in contact. I will just show you the nodes. So here you can see one node is in contact with your pile. And I will hide those nodes. Yeah. So this is one approach where you're considering the piles as a beam element and the rest of the things as solid elements. But now let's say I don't want to consider the solid raft as a solid element. I want to consider it as a shell element because there can be you might be interested in knowing the bending moment in the raft as well, right? So when you go for solid element, you cannot find the bending moment in the raft, and there is an alternative approach. But apart from that, you can consider the raft as a shell element as well. So now I will show you how to consider the raft as a shell element. So I'll just hide this one, raft as a solid, and I will unhide all the solid elements. So here, just hide this one. And here we have an extract option. So using this extract option, we will extract this 3D mesh, already first layer 3D mesh. So we will consider that mesh, and we will we will extract as a 2D element. So this is a 3D mesh, and we are extracting a 2D mesh out of a 3D mesh. So that 2D mesh is given with a raft of shell elements. That's a raft shell. So now I will show you the different properties. So here we have a raft as a shell element, and here we have a pile as a beam element. So this is a 2D element, and these are 1D elements. And we have a soft rock at the bottom, which are in contact with your piles, and we have a dense sand, and we have medium sand. And if you want to check the thickness that I have provided, so you can go for the check thickness. So this is the thickness, the virtual thickness. Here you can see the thickness that we have provided is of 1 meter. And if you don't want to use the shell element, you can directly use the raft as a solid. So the only thing is we have developed a different method, but it is up to you to activate your own elements while doing analysis. Now I will show you how to use the pile as a beam element plus pile interface. So I will be showing you how to use the pile, beam, and pile interface. So the first one is done, and the raft as a solid element and raft as a shell element is done. So we will see how a beam element and pile interface can be modeled. And in this model, I will be considering, let's say I will be considering a solid element as a raft, and then the pile as a beam element, and then the pile interface will be applied to it. So we'll see how to model them. So I will hide all these. We are no longer interested in them. And just unhide your work plane and the axis. So now let's go for 1D lines again. So here the pile is a beam element, and then further beam element and interface will be applied. So we go to 3D. We need to go to 3D, and let's say 0, comma 0, comma minus 10. So that's the length of the pile. And now we are going to translate that pile. We can use the translate option. If you want to translate in a different direction, you can use this vector. So let's say I want to translate in this direction, and let's say I would like to do it with 1 meter difference, let's say 2 meter difference, and I would like to say copy. And along this vector, that will get distributed. So this is how you can even translate it in your own vectors. But let's say I would like to translate in the y direction, and the copy with the 2.5 meter distance, and let's say the times of 3. So this is one set of piles. And now we need to select all these piles, and we will translate in x-axis. Yeah, these are your piles. And now what we do is we will model a raft. What we do is we will go for perspective view so that you can even find the piles when you go into a top view. So let's
Yeah, so this is my raft, and yeah, in the same way, I will be modeling the soil boundary as well. Let's say this complete boundary is my soil boundary, and now we will extrude the solids. So here we have an extrude option. What we do is we will extrude the solid, go to basic, select your line, and select Z axis, and the length as 1 meter. So that is for raft. And now the basic, you can, I will be directly extruding for around 15 meter, and then I will show you how to divide the lines, divide the solid using different approaches. Let's say the entire soil layer is for 20 meter depth, and we have one layer at 5 meters and one layer at other 6 meters and so on. So that's how, let's say we have an option. And let's go for the surface, make face option. We will translate this surface. We will cut this solid using this surface. So that's the idea. Select the surface, and first suppose I'm going to copy it in a non-uniformly. So first thing is minus 5 meters, comma, and then from there it will be like around minus 4 meters depth. From, if you undo it, so from the first point it is minus 5 meter depth, and from this point it is 4 meters depth. So that's how you can non-uniform copy it, and we just say OK. Now we have solid divide option. So using this solid, we will select the surfaces and we just divide them. So we have all the 3 layers of the soil. So there are many ways to model, and this is one single particular way. And now we will auto connect all these solids. So select all your solids and then just say OK. And one more thing is here we no longer interested in imprinting the piles onto soil layers because we are going to provide a pile interface. But let's say we are interested in intersecting your lines with your raft, imprinting your lines with the raft, because we know that there can be an rigid connection, there can be hinge connection, there can be let's say a sleeve connection between raft and the pile. So we need to model each and everything, and I will show how to do it. But at first we need to imprint these lines with your raft. Only raft, not all the soil layers. In the previous model, I have imprinted your lines onto each and every soil layer, but here I'm only imprinting your lines with your raft only. So here this symbol represents that they got imprinted, and even you can check whether they're imprinted or not. So you can go for this check duplicate points, and if you apply it, you can see these are your different points. So that's how you can define them. And now I will show different ways to model. I have shown you 2 ways to model, but now at first we need to define the pile element and the pile interface to it. So let's go and define the pile interface at first. So here we have pile interface definition. So when you go to the create option, you have a different 4 categories. One is isotropic category, orthotropic, 2D equivalent, and interface and pile. So we go to interface and pile. And in the model type, we have a pile interface. So we need to input these 3 values. Let's say we have ultimate shear force, and we have shear stiffness modulus and a normal stiffness modulus. So we need to calculate these values, and we need to use them in this analysis. So let's say I'm having ultimate shear force of like around 1000 kilonewton per meter square, and shear stiffness modulus as 1 lakh, and normal stiffness modulus as 2 lakhs. But I will show you what are the different ways and what these three inputs actually suggest in reality. Actually represents in reality. I will show all the three inputs and we'll name them as pile interface. So we have ultimate shear force, we have shear stiffness modulus, and normal stiffness modulus. I will show all those three now. So let's go for help manual. If you just directly click up F1 and you can find this help manual opening. And we go to material. Here we have a pile. So first, suppose you have a pile load test that has been done. So in that load test, you can find the relative displacement versus traction. So the friction versus relative displacement graph can be drawn. And so the graph can look like this. So this is one way of pile load test results. So what happens is with the load, with the increase in the traction, the relative displacement can vary like this. And this point where it is starting, where it is changing its position from elasticity to plasticity, that can be our ultimate shear force. So that is our ultimate shear force. So we have three inputs that needs to be done, inputted in the software for pile interface. One is ultimate shear force, shear stiffness modulus, and normal stiffness modulus. So we have ultimate shear force, and this is our shear stiffness modulus. So the slope of your linear curve, that means till elasticity curve. So that is our shear stiffness modulus. And now let's say we need to import normal stiffness modulus as well. So the normal stiffness modulus is nothing but lateral subgrade modulus reaction. So you can directly calculate and you can directly input it in the software. And there are many ways to calculate as well. First, suppose if there is no pile load test results with you, then we have three ways to calculate those inputs. So first is by using a loading test results, that is pile load test results. And the second one is by using ultimate shaft resistance. So first, suppose using different codes, you have calculated ultimate shaft resistance. Then you can directly input that ultimate shaft resistance, and that ultimate shaft resistance upon the lateral displacement criteria will provide you with the shear stiffness modulus. So here you can suppose 150 kilonewton per meter square is my ultimate shear force. So that upon my let's say 25 mm is my criteria. So that upon by 25 mm will provide me with 20,000 or will provide me 60,000 kilonewton per meter cube of shear stiffness modulus. So similarly, you can calculate lateral normal stiffness modulus or lateral subgrade modulus reaction. And first, suppose you don't have resources to calculate your ultimate shaft resistance, then we have the Blizzard formulas using your reduction factors and using your the interface properties. So here we can calculate using this formula, and here for each formula what is the value and the corresponding definition has been given. You can use this inputs to calculate your pile interface parameters. So that's how we have calculated. But let's have provided some interesting values. Let's say. And apart from that, we are also interested in providing the tip resistance to the model. So we go to property tab and we go for other, and here we have a pile tip property. So this is my pile tip property, and what we do is we will provide a certain pile tip resistance. So the tip bearing capacity by calculating using analytical methods or by getting it from the pile load test results. So you'll be knowing the pile tip bearing capacity. First, suppose I have a pile tip bearing capacity like around 2000, since it is a soft rock, and then the tip spring stiffness will be your tip bearing capacity upon your settlement criteria. So let's say that is 2000 upon 0.025, that means 25 mm. So you'll be getting somewhere around 80,000 kilonewton per meter. So this is my pile tip. So now I have defined the pile tip and I have defined the pile interface as well. So we need to apply those pile interface and pile tip to your lines and so on. And one more important thing is we are providing the section property of beam element to it, but we are not using like imprinting option of your piles as a beam element to your soil. We are providing pile interface in here. So this is the best approach in order to model the soil layer. So we have already made sure that these are in connection with each other. We will check it once again. Yeah, the soil layers are not connection in the with the raft. So we will go for auto connect option with Boolean condition, the Boolean method. And now we will check the duplicates. Yeah, so we are having the co-phases. That means those are in contact with each other. Now we will mesh the soil layer along with the raft. So we'll first mesh the raft. So let's say it's of 0.5 meter, and this is solid raft. We will use hybrid mesh now. So since we imprinted your piles with your raft, you can see the common node between your raft and your pile. So that's how you can see your common node. If you don't imprint your lines with the raft, then there won't be any common node. But we need to imprint it. As of now, it's a rigid connection, but I will show you the different upcoming scenarios as well. Now, the first layer, let's say it as 0.75, and we will be using a medium sand 2. It's just taking time. I think I have provided 0.75 meter mesh, I guess. Yeah. Yeah, so it has just taken time to change your dimensions from 0.75 meter at the boundary to 0.5 meter at your raft, since we have given the 0.5 meter mesh size of the raft. So now I will be considering 1 meter mesh size, and here we will use the dense sand, and we will say apply. And then for the last layer, we'll be using soft rock, and that will be given with a certain, let's say 2 meter mesh size. So next time I will be meshing all the soil layers at once so that it may take less time. And then at last we will change the properties. So now let's say 2 meter, and this is hybrid measure, and this is the soft rock property. Yeah. So now we can see there is a raft and there is a 3 layers of soil. And now we'll proceed for meshing the piles. So we will hide all the soil mesh sets, and I don't want to have this rectangle. I'm just hiding the rectangle. And now we will provide a 1 meter mesh size. So select your, one division. Select all your piles, and we will only provide one division. So only one division is being provided right now. And here we are providing the pile beam element, one division only. So now from top to bottom, your entire pile is being divided into one element. So one node at the top and one node at the bottom. So it means a complete whole one single element. So now, as of now, your raft is in contact with your pile in a rigid way. But now we'll be providing pile interface to this your beam element. So here we have a pile tip. So when you click, you can find this pile tip. And I have defined the material, but I haven't defined the property. So we will define the pile property. So we go to 1D. Here we have a pile and the pile interface. And let's say this as with name as pile interface. Close. And now we go to pile tip. So select all your elements. So here we have an intersect option during selection. So I'm just hiding again. So these are your pile elements, pile beam elements. And now we are naming them as pile interface and say apply. So now what you can see is when you divide, at first when you create a pile beam, it is only having one division. But when you apply the pile interface, it will be divided between your soil into many nodes. So you're dividing, whenever you apply pile interface to your pile, it divides your entire pile beam element into many nodes. This means this will be done according to your soil elements surrounding it. So it will be automatically considering the skin resistance because of these nodes. Now what I will do is I will just hide these nodes, and I would like to provide pile tip. So we go to pile tip, and pile tip at the very bottom. I have selected some other many nodes. Yeah, so these are your different pile tip nodes, and we'll say okay. So here the pile interface is defined and pile tips are defined. But right now, whenever you apply your pile interface to your piles, so it will be dividing the common node. Here we have a common node earlier, but now there will be two nodes in here because we have applied the pile interface. So this means the pile is in like a free condition, but we don't want the free condition. We want the pile to be rigidly connected or hinge connection between raft and the pile. So what we need to do is we need to go for the merge option and select all your pile elements. So these are your different nodes, and I will say to find what are the different nodes which are not coming into this tolerance. So I will click on find, and here I can see there are red dots which represents that these nodes are divided, and I'm going to merge these nodes at the center location. So now again, these nodes are in rigid connection. But let's say I would like to provide a hinge connection between the raft and the pipe. What I will do is I need to provide some element parameters. So what you can do is you can go to the create, and I will provide some end releases. Here, we need to go to parameters. And here we have add end release. So for the top layers, let's say for the top elements, so these are your top elements of your pile. And since it's a hinge, since it is a hinge property, since it is in a hinge property, I would like to let the software know that there is no rotation being transferred. So the NDA and NB are nothing but the first at the top it is an NDA and it is at the bottom it is NB, and it may change based on your local axis direction. So let's see the local axis. So here you can see the red axis is your x-axis and it is going downwards. So that represents that the first one is NDA and downward is your NB. So if your x-axis is towards the top, then bottom one is NDA and top one is NB. So now I'm letting the software know that all the top elements are being end released, and sorry, I have considered file interface. Yeah, 1 minute. That's my mistake. Now I will consider, I'm hiding the file interface and I will provide only beam element. Only to the beam element, I'm applying your RXI by RJ. Yeah. Sorry. So this is file and I will see the direction. RX by RJ. Yeah. So I was mistaken. So here you can see the top one is NDA and bottom one is NB. And here I'm providing on the top end. So on the at NDA, I have provided the hinge connections where the moments are not going to release. And this is a hinge type connection between your raft and the pipe. So in this model, what you have seen is you have created a raft as a solid element, and I've created the piles with the beam element for structural condition and as a pile interface element to provide realistic support of resistance using the skin friction and tip bearing resistance from the soil. And then I modeled the soil layers as it is, and I provided hinge properties at the top. And first, suppose, let's say I still want to know what is the bending moment on this raft. I'm not modeling it as a shell element, but still I would like to know what is the bending moment on this raft. So in order to know that, there is one more property called a gauging shell. So what I will do is this gauging shell property will be applied to this solid raft. Since solid is having only 3 degrees of freedom in translation, so there is no moment a degree of freedom. So it cannot be able to calculate the bending moment. So hence, what I will do is I will be applying the gauging shell element. Here, using the create option, you go to the gauging shell and you need to choose the solid. Let's say this is the solid. And on the top face, I would like to provide a gauging shell property. So let's name it as a gauging shell. And it is along global rectangular. And let's say, okay. So now a gauging shell property has been given. I will show it. Yeah. So on the top and bottom, I have given the gauging shell. If you don't want the gauging shell at the top and the bottom, means you can do whatever you want. Here, now the bending moment at the bottom of your raft and on the top of your raft. You can see the bending moment in both the scenarios. If you don't want, you can delete one shell element. Let's say I'm going to delete a 2D shell element at the bottom. So this is gauging shell. It's not shell element. It's a gauging shell element. It is not having any structural property within, but but it will generally provide the bending moment and the shear forces in your raft, since it is acting like a cover to your solid raft. So this is my solid raft, and on the top of it is a gauging shell element. So that's how you'll be providing different 1D beam element models. So here in the first model, we have considered the beam as the pile as a single beam element. And then we imprinted that beam element to your soil layers, and then we meshed them. We directly meshed them using 1D mesh for soil layers and 1D mesh for the pile elements and 3D mesh for soil layers. But in the second model, what we have done is we have created the raft as an solid element and the piles as 1D elements using the 1D curve. And then we haven't imprinted the lines to soil layers, but we have imprinted them to years raft. And then we provided hinge connection over there. And then we provided file interface, and then at the bottom we provided file tip. So this is the second one is the very best approach in order to consider the properties and then modeling of your files. And then we will be seeing how to model. Let's say I would like to model an file as an volumetric file. And before going to it, let's say I would like to provide an interface between raft and the soil. So what I will be doing is I will be going to interface option. So here we have an interface option. And you go to plane interface and add the element boundary. So this is my solid, the raft. So you can consider the two types. If when you're considering element boundary, that means the interface will be provided at the boundary of this mesh set. And if you want to consider using type as the mesh set type, so you need to consider both the mesh sets and the common faces between these two will be provided with the interface element. So both the ways work fine, but it is up to the applicability of different types of interfaces in different positions. So I will just consider element boundary for now. I will select the element raft and I will be using the wizard. Let's say here the layer is a soil dense sand layer, and I will hence I'll go for around 0.8 reduction factor. This is concrete and this is the sand. And let's say we'll create rigid link and say okay. So now there is an interface. This is an interface between your solid raft, so between your solid raft and between your sand, so that you can able to find the slip between these two materials. So you can find the slip forces, the tangential forces, and then you can find the tangential slip related displacements as well. So that's up to us how we need to model them and how we whatever the results that we are interested in. And apart from that, I have applied the gauging shell on the top as well. So this is it for relating to 1D beam elements. Now I will show you how to model the volumetric files. So we will hide all these things and I will show you how to model volumetric files. So let's go for the next quadrant. Let's say here. We go to geometry, and here we are not providing any section properties, but we are modeling directly the volume as we are directly modeling the section itself. Sorry, and let's say this is my center of my pile, and I knew that the diameter of my pile is just 0.75 meter, and we need to input the radius. So let's say the radius is 0.375. We will create a new mesh set, new geometry set, volumetric files, and say apply. So here we have files, and then we will translate this circle. So before translating, we will extrude this circle, and then we will translate it. So that will be even easier. We select the edge, and we will extrude it in Z direction. Let's say the length is 10 meters, and say apply. So now we have a volumetric file, and we will translate this file. Y direction, let's say copy to 2.5 meter distance, and we will do it for 3 times. Apply, and we'll select all those solids once again. We'll translate them in X direction. Now again 2.5 meter and 3 times. So again we have So right now we are having like around 16 volumetric piles. So we will create a raft now. We can directly create a make face. So let's then creating face option. Sorry. Yeah. And now we will be extruding our raft to 1 meter depth. Give me a minute. Yeah. So here we will be selecting the raft and we'll be extruding it for around 1 meter. Yeah. And now we'll create a new face once again for the soil layers. So that will be huge. Let's consider the mesh, the soil size from here to here. Select your point and the direction as the direction, and we will directly create a minus 20 meter. And now we will divide those layers. So like how we have done in the second case. So we'll translate it. Non-uniform translation, -5, comma, -4. Now we will cut the solid. Yeah, so now you can see all the soil layers has been made, and we need to make sure that all the soil layers are in contact or not. So hence we need to go to auto connect. So here we have an auto connect and the method is fully in operation. So select all your solids and then just say okay. Yeah, so now we will check the duplicates. Yeah, here you can see we got the 3 layers of soil and we have around 16 piles. So all the piles are in contact, hence we have orange faces, and all your layers are also in contact, and the pile raft is also in contact. So hence we can proceed for meshing. So that's how we will check them. So at first, what I will do is I will carry on with the mesh. I will carry on with the meshing of piles. So I'm hiding all the soil layers. And so let's mesh your piles first. So if you're running and construction stage analysis, in the first stage it's an in situ stage as always, and what you do is you will be modeling these piles as an let's say soil material and not raft material. So hence, because it is an in situ condition, and when you go for second condition where you're inputting, where you're constructing piles, in that stage you will be changing the material property of soil to the concrete. But right now we'll be running only simple nonlinear static analysis. So we'll be providing directly. The raft solid is a concrete property, so I'm providing the same, and I will name it as piles. So if you observe it, I'm always coming from the always doing the meshing from a point of high concentration of stresses. So in here, we will be having more stress concentration in the piles and the raft. So we need to first mesh the piles and the raft. So now I have meshed the piles. Now we'll mesh the raft. So with the raft as solid 3. So we have 3 more layers. We'll select all the 3 layers, and let's say we will apply the mesh size, a common mesh size of 1 meter. And we will be providing medium sand, but we will change the parameter name. So we will change the material that is applied to second and third layers. Yeah. So here you can see the 3 layers has been formed, but we will change the 3 layers. So here we have the last layer, and we will change the name at first, and this is a soft rock 3. Apply, and the second one is dense sand 3. Now we will change the parameters. So go to 3D, and here change property. Select the soft rock, and we provide soft rock. So you select a soft rock mesh set and provide a soft rock property. Similarly, select your dense sand mesh set and provide dense sand property. Yeah, so here you can see the entire model has been done, but now we are left with interface. So we will be applying the interface between your piles and the soil at first. So here we have an interface option. So here we have different piles. I'm directly selecting the piles from the work tree. So I have selected the piles from the work tree. But at first, we need to choose the plane interface. So select all your piles and choose the visit. Let's say 0.8 and provide interface 1. Yeah. So here you can see, I will just hide the dense sand and the medium sand. So here you can see an interface material is being formed between your piles, the volumetric piles, and the soil layers. And when you see the medium dense sand, the first layer, the piles and the raft are sharing same nodes. So there are same nodes in here. So what happens is whenever you're creating the interface between the raft and the first layer, then you might face some problem. So in order to overcome that, I'm going to merge only the top nodes. So we have pile and we have created the interaction between the pile and the soil layers, but the interaction between soil and the raft is still there. So what we do is we will merge these points wherever the interface was formed, and I'm merging them. So now here we can see the raft has been so now the interface has gone. So at first there was an interface symbol. Now there is no interface. So now what we do is we will create a mesh, the interface between the raft and your first layer. So go to interface. You go to plane. So you can choose. So now you're providing the interface between the raft and your first layer. So hence, I'm going to the type called from mesh set. So I'm choosing the raft, and the first layer. So you can choose directly from element boundary as well, so that's not an issue. But if you choose from element boundary, there will be an interface generation between your raft and your piles as well. So, but from between raft and the piles, it should be rigid in contact. So hence I'm choosing this option from mesh sets. So only the common faces between the first layer and the raft will now be provided with interface. So we will provide again a 0.8 and we'll use plain interface. So now the plain interface will be formed. And again, we need to provide boundary conditions as well. I will show you how to provide boundary conditions. So since this is not symmetric, since we have 3 different models at the different spaces between them, we need to provide boundary conditions separately. I will show you how to provide the boundary conditions as well. Actually, a model is running in my PC, hence my PC is a bit slow. Sorry for that. A big model is being run in my PC and it is making slow. I'm sorry for that.
What is your PC configuration?
Right, my PC configuration is bigger only, sir. Like I'm having 16 GB RAM and 2 TB hard disk and i5 Intel i5 8th generation. And
Okay.
the number of cores is only 4 cores. But actually, what happens is in this software, you are having an advantage. Like you can choose all the cores at once so that the model, the analysis speed can be increased very high. I will show you that option. So in my previous model, I have created that to choose all the cores of the PC. So hence it is taking time.
And will it be run in i3?
Yes, sir, it will run.
Okay.
Even it can run. It can run even in the Pentium chip as well. It's not an issue.
Okay.
I will just show you the option to increase the number of cores. So this is a very good option so that you can increase the number of like you can decrease the time for analysis. So you go to analysis and you can directly increase the number of processes. So right now, my PC is having 8 logical processes. So I have inputted the entire 8, and I asked the software to choose the GPU acceleration as well. So right now, my PC is running full 74%. Sorry for that. Yeah, now the interface has been created. We'll just hide the medium dense and then the graph. So here you can see the interface between your raft and soil, but there is no interface between the soil and the raft and the pile. So there are many interactions between the pile raft, right? One interaction is between the piles and the soil. So you have done it by using your pile interface, and then you have interaction between the raft and the soil. So you created an interface in order to realistically provide the interface, the slippage and the normal force transaction from the raft to the soil. And then you have the interaction between the raft and the piles. So between the raft and the piles, it's rigid in nature. If you want to provide any hinge type of connection, then you can provide it. But right now, it's rigid in nature. And and then you'll be having one more interaction called pile group effect. So since it's a 3D model and you have considered all the models at once, so now you can have the pile group effect as well. So with one single thing, you can able to model all the process. So that's how flexible this Midas software, FEA NX and GTS NX software. So here you can see these are your different models. Now, what I will be doing is I'll be providing the boundary conditions. So we go to static analysis tab, we go to constraints. So at first, I'll be providing for the case 1. I'll be choosing, we go to advanced tab. Case 1, and let's provide, consider all the vertical boundaries in X direction. So provide normally fixed. So these nodes are going to fix in X direction. So those are normally fixed. Apply. So now we go to top view. We will be providing the same, but this is for Y direction. Apply. So now we go to front view once again, and at the bottom it is completely fixed. So TX, TY, and TZ. Apply. So similarly, we will be providing for case 2. At first, we will choose your X-axis. Sorry, the nodes in the boundary elements for along X direction. This is for X, and now we will choose for Y. So after this, I will show you the results so that it will be more helpful. The different types of results that you can find in the pile raft analysis using different approaches. So here we'll provide for TY. And now let's consider at the bottom. So here this TX, TY, and TZ. Apply. So now case 3. So this is for Y direction. So this is for X direction. So now all the boundary conditions has been given, and the model is done. I haven't applied the loads, but I know you knew about how to apply the loads. You can directly choose the pressure, and if you want to apply the force and everything can directly be applied. So let's consider the analysis case. So go for nonlinear static analysis, and we will choose volumetric pile set first. Volumetric piles. I'm only going to for 3 numbers. So layers are done, and we are going to provide interface plane interface, and then we have different piles. So we need to add this raft, the solid raft 3. Yeah. So these are your case, and this is for case 3. And that's how we are defining only the volumetric case. So the first and second cases are no longer run in this analysis. So similarly, you can create another case. So let's go for pile beam plus interface. Yeah. So here we'll be having dense 2, medium sand 2, and we will be having the soft rock 2. And in this case, we are going to have a plane interface for raft, and we have pile beam 2 and pile interface 2, and the raft raft solid 2, yes. So this is the one, and we have applied gauging shell to it. So gauging shell. So these are your elements, and we have case 2 boundary sets, and that's okay. Similarly, you can go for the first elements analysis cases. So that's how in one single model I can able to do all the kinds of pile raft analysis, whichever is possible. Now I have already run some analysis. I will show those results to you. Now, at first, I will be showing you the results of the settlement, and then we will see the results of, let's say, the axial forces, the shear forces, and then the skin friction along with normal forces. So I have applied certain load on this pile. So let's go for TZ settlement. So auto range it, and I would like. I don't like the smooth curves, if suppose, so we will change it into fringe so that these contours can be seen. And if you want to see the contour lines, then even this can be seen. So that's all up to us how to represent. So let's go for undeformed shape. So this is the undeformed shape, and I will show the cut behavior. So here you can see. And that the piles, because of the piles, the reflection, the settlement is actually moving, the settlement contour gone downwards. So because of your piles, and similarly, you can go ahead. Yeah, and here in this case, there is only raft applied. So you just go. So, and in this section, there is only raft that was applied, so hence only very less contour. And because of piles, we can see more the contour which is increasing and which is known. So that will obviously come. Now, I will hide all your soil. So now the soil has been hidden. We'll see the pile forces. So the tangential x represents your skin friction. So here you can see that it started from 0 and it reached till 118 kilonewton per meter. So from top to bottom. So in this pile and this pile, you can see the results difference. And now let's say I would like to know the normal force acting. So the normal force in each pile. Let's this is now I will just hide all the unwanted things. Yeah, getting shell as well. And main piles. Yeah, so here you can see this is the normal forces acting on your piles along a local y direction, and this is the normal force acting on your piles. So here you can see it started from at the top it's like around 48, and at the bottom it's somewhere reached only 20. So because that's in kilonewton per meter. So this is a normal force acting on your piles because of the lateral force that you have applied and so on. And now we'll see is a pile tip. This is an unvarying resistance in each and every pile, which is being coming in this model. We have like around 143 kilonewtons in each at the bottom of your pile. So now you can see the skin resistance. You got skin resistance, you got tip bearing resistance, and you know what is the normal load acting on each and every pile. Now we'll see what is the axial force. So in this situation, the pile is also resisting some load, the soil is resisting in the form of skin friction, the raft is also resisting, and the tip bearing resistance is also resisting. And the pile is resisting in the form of axial force, and here we have the maximum value of around 140 kilonewton. And the shear force, let's say if you want to provide a, and then if you want to go for bending moment, so the bending moment, the maximum value is like around 233 kilonewton meter. That is along local y axis, and this is along local z axis. Here, the maximum value is 228. Since it's symmetrical, you can find both almost same values. Yeah, apart from that, you can even find the bending moment stresses according to von Mises, according to the shear stresses, the maximum axial stress. And I will show you the failure zone. Let's go for solid strains and the E equivalent. So this is how the E equivalent will represent your failure zone. And if you activated as maximum shear in your output control. So in the output control, you can control your results, what type of results you want. So if you activate the strain, then you can find the strains in all the directions, X, Y, Z directions, and even the shear strains also. So now we'll see how the maximum equivalent strain looks like. So this is how the failure plane looks like. The bottom boundary is not sufficient. We need to increase the boundary in this particular model. But since the value is not that changing, so but this is fine. Yeah. So this is how we can find different results. And one more thing is you can take the snapshots of each and every result that you're interested in. If you're interested in a pile tip resistance, you can directly use those values, and the software will automatically take the snapshots of that results, and that can be posted in the Word format or in images, and that will be stored in your at any place where you have output created. So that's all for today. If you're having any questions, kindly let me know, sir. I think that today's session is a bit longer.
Yes, and you have showed so many things. You have described a lot of things to us.
Sir, I will be sharing the recording session as well, so that will be helpful for you later on.
Yes. Okay, and I will share the 27 topic which we will discuss on 27th.
Yes,
okay.
Yes.
Today I will mail you.
Yes, sir, please mail me and then I will share that with my colleague, and he will prepare the model files accordingly, and he can share that with you in the session.
Okay. Chinmay will be giving that session.
Yes, sir. Chinmay will be giving the last session, 27th session.
Okay.
Yeah. So if you're having any other questions, kindly let me know.
Okay. Right now, no issue. We will check